Deep Blue that beat Kasparov at chess in 1997 essentially just brute forced it, right? So essentially just a supercomputer, that could search hundreds of thousands of moves per second. It predicts what's going to happen next in the world and then adjusts the weights, the parameters of the network to make a better prediction next time. The brain is fundamentally a neural network, and the architectures which, kind of power modern deep learning are neural networks. Getting the models to say things that we kind of agree are true is a problem, and it's a technical problem, it's a conceptual problem. I think the history of AI has been history of people saying that'll never work, and then it does.
Hello and welcome. I'm your host, Sam Knowles. And joining us today is Chris Summerfield, the Professor of Cognitive Neuroscience at the University of Oxford. Chris leads the Human Information Processing Research Group in Oxford's Faculty of Experimental Psychology. He's also Research Director of the UK AI Safety Institute. On his faculty page, Chris describes his research focus in this way: "My work lies at the intersection of cognitive science, neuroscience, AI research, and social science. In my research group, we study how humans learn and decide from a behavioural, computational, and neural standpoint." Indeed, Chris and his colleagues use neural network models as theories of human learning and cognition, and as objects of study in their own right. Chris was trained in psychology and neuroscience at the University College London, Columbia University in New York, and the École Normale Supérieure in Paris. His work is funded by grants from the European Research Council, the Wellcome Trust, and the National Institutes of Health. Now, I came across Chris recently when he was speaking at the Charleston Literary Festival earlier this year, alongside Christine Rosen from the American Enterprise Institute. Their debate on the pros and cons of AI and the consequences of us living increasingly mediated lives was titled "Strange New Minds." And minus the first word, these, this is also the title of Chris's seminal, very readable and mass market book published earlier this year, subtitled "How AI Learned to Talk and What It Means." Now, at Charleston, I was a bit of a keenie in the audience. I shot my hand up and asked the first and thankfully memorable question on humility and uncertainty markers in AI, a topic that I'd like to come back to a bit later. And I followed that up with an email the next day, which, thanks to Chris agreeing to appear, is why we're here now. And it's great to have you with us today, Chris. Welcome to Data Malarkey.
Thank you. It's lovely to be here, and thank you for that generous and highly accurate introduction.
So I wanted to ask you if that was a good narrative and if of how you've got where you are today. Is there anything I've missed out? Anything I got wrong? It's your chance to put the record straight.
No, it's fine. I mean, I guess, kind of you're absolutely right. So I'm trained as a cognitive scientist and neuroscientist, and for years that's sort of mainly what I did. And so over the years, as society has got more and more excited by AI, I got more and more excited by AI, and that so for many years I was a researcher at DeepMind. And I was actually one of the very first researchers to join DeepMind. I was there for 12 years, at least. And I left in 2023. And so and since then, my job at what's now called the AI Security Institute in government is about AI safety. So I'm sort of spending more and more of my time thinking about the implications of AI for society, and kind of that sort of counterweighting the other work on how humans learn and decide. So yeah.
So I guess, and this is something I hadn't thought about before then, but I guess your many references to the ancient Oriental game of Go in your book are in no small part related to your time at DeepMind, right? Because of AlphaGo and that amazing program.
No, exactly. Yeah. So I was there. I was there right from the start. So both the first, I guess, most important landmark kind of like result from DeepMind was training models to play Atari games, which was, sounds quaint now, but was extremely impressive at the time. And then it was a lot of fun to be part of DeepMind when Go was happening, because of course there was, members of the company had sort of privileged insight into kind of that happening. And then, kind of like by the time protein folding happened, which was another amazing thing that DeepMind did, the company was so big, I didn't even know the people involved, basically. So there was already thousands of people by then. But, of course, DeepMind, after the Google acquisition, grew to be really big.
In a very, very amateur way. I played a little bit of Go with my dad in the 70s and 80s. I've taken it up again recently. But watching poor old Lee Sedol's face, the grandmaster Go player, when he loses 4-1. Sorry, spoiler if no one's seen the AlphaGo movie. But looking at his face and just seeing his sort of sense of humility. An amazing thing to do, and extraordinary that for such a relatively simple game. I know there are said to be more potential configurations than there are known atoms in the universe on the 19 by 19 board, but for such a potentially unsophisticated game, it took something like 19 more years for AI to be able to defeat humans at Go than chess.
That's right. Yeah, exactly. Yeah, 1997 to 2016. Yeah, that's exactly right. But I mean, I think it wasn't that, what happened in that period was computers got a lot faster, but it's also true that the algorithms that were used to solve Go are qualitatively different from those that were used in chess. Chess is the Deep Blue that beat Kasparov at chess in 1997 essentially just brute forced it, right? So essentially just a supercomputer, that could search hundreds of thousands of moves per second or potential moves, and then just choose the one that it thought to be best. AlphaGo did do something a bit like that, but it used a neural network to then predict which of those moves was going to be the most successful one. And there's that really exciting combination of the sort of old school like planning and search with this, what was, at the time, the kind of very, very new and exciting idea that you could use a neural network to solve a game, a complex game. That was the thing that really blew people away, I think.
Oh, marvelous. Now, listen, in contrast to many of, let's say there's a current crop of AI doommongers, your book and also your talk at Charleston offer a strikingly optimistic view of AI's cognitive capabilities. Why do you think that the narrative of AI as a parrot, indeed a stochastic parrot, as you say many times, has endured so long, despite mounting evidence to the contrary?
This is not a new debate. So, of course, throughout the history of AI, there has been exuberant excitement around leaps in progress. And at each stage where AI has done something it couldn't do before, there have been people who have popped up and said, well, that's not nearly as impressive as it looks. And, I think that the bold truth is that both sides are always right. It is always true that the advances are kind of impressive and eye-popping. And, if you put yourself back, you wind back the clock 5 years or 10 years and say, we would in, X years time, will have a model that can talk to you as fluently as any other person on the planet can. Most people would have said, well, I think that's impossible. So it is, we have to, remember that it is an astonishing discovery. I mean, in particular, the latest wave of language models. But at the same time, it's also true that these models are nothing like people. They lack, most of the really important machinery for surviving in the world, mainly because they don't have to survive in the world. But all the stuff that maybe we don't think of as so cleanly associated with, or as cleanly associated with intelligence as maybe being very eloquent and solving reasoning problems or playing chess, but things that are nevertheless incredibly difficult computationally, like moving your body in a way that, stops you from falling over, or being able to navigate a social situation, so social cognition. So these are just two examples of things that, the models are not really able to do those yet in the way that humans can, at least.
And you argue that prediction is at the heart of both LLMs and also human intelligence. Could you just unpack a little bit about how just predicting, I mean, in the case of LLMs, predict the next token, but how just predicting actually gets large language models surprisingly close to something that we might call thinking?
Yeah, well, I mean, of course, nobody quite knows the answer to that question, but I can give you some version of it. So, if you wanted to take a kind of deflationary stance about current AI, then one way that you might do that is by appealing to the simplicity or the apparent inadequacy of the mechanism that the model has for learning new information. And that mechanism is very, very simple. It predicts what's going to happen next in the world and then adjusts the weights, the parameters of the network to make a better prediction next time. And that's something that a class of machine learning tool that's often called a generative model, that's what it's trained to do. And of course, why would we think that that's inadequate? Well, we probably think that's inadequate because it reflects just one of the different ways that you can conceive of an agent learning, right? Of course, we learn in lots of other ways. We learn, by forming goals and seeking to achieve those goals by trying things out in the world. We learn based on the value of the reinforcement value. We learn by teaching each other. We learn by, thinking abstractly and reading books and all of these things. And it's very easy to say, well, how on earth could you ever acquire intelligence by just trying to predict whatever comes next? And, that sounds very reasonable. But if you think about it, so from a neuroscience standpoint, there's just a fundamental principle, which is that if you want to learn something, not the only way, but basically the most effective way to learn something is always going to be to have a guess and to kind of correct that guess a little bit in the right direction on the basis of the information that you get. And actually, even many of those other types of learning that we're talking about, if you think about reward learning, that's also how we learn from rewards. If you think about playing tennis, right? You start out and you're really bad and the ball goes everywhere and you get all of this negative feedback and you gradually adjust your tennis swing until you're, Bjorn Borg or Novak Djokovic or whoever, if you do it enough. And the same is true in almost every domain. And the brain mechanisms which allow learning are themselves based on fundamentally based on predictive mechanisms. So you get a bit of information and you try and work out what's missing or what's coming next. And the brain does that and it gradually adjusts. So, prediction does sound overly simplistic, but at the same time, it's basically how the brain works.
Very good. Very interesting. Now, listen, you've hinted at a couple of ways in which, clearly, you talk about kind of motivation and the lack of sensory modalities in large language models. But could you give us maybe three ways in which, and obviously here in terms of prediction too, but can you give us maybe three ways in which human brains and the current crop of large language models and our thinking are similar, and maybe three ways in which they're fundamentally different? Is that a bit too?
I'll give you some ways of each. Yeah, I can't promise you three. Yeah. So what's similar? I think structurally there are similarities and differences, right? So if you think about the structure, so the brain is fundamentally a neural network, and the architectures which power modern deep learning are neural networks. So neural networks consist of sets of units which encode they encode values, which in the brain is how much activity is being generated, and in a neural network, artificial neural network is just a number. And those units are connected together by connections that have variable strength. And in neural networks, those are weights, and those weights are, again, just numbers that dictate those strengths. And in the brain, they're synapses, and there are a number of factors that dictate synaptic efficacy, but broadly they boil down to various forms, how many receptors there are and how vigorously they're released, right? Which is determined by various protein synthesis mechanisms. So there's a similarity, there's a structural similarity. But there's also a big structural difference, which is that, if you think about the way that particularly transformer networks, which are the workhorse of modern deep learning, particularly large language models, the way they work and the way the brain works, the dynamics of activity are incredibly different. So, transformers, what they do broadly is they take some information, they very cleverly learn what goes with what. So the weights are roughly encoding some sense of what goes with what, and then they make a prediction about the next thing. So through the network, there's just one sweep of information, input through to output. The brain is not like that. The brain is recurrent. So what that recurrence means is that their patterns of activity in neural networks become they display interesting dynamics. They are self-sustaining in many ways. So neurons will excite neurons that will excite other neurons that will excite those first neurons in the first, and so you get these loops of activation. So from a physical standpoint, there are both similarities and differences. And I think, kind of from when you look at a behavioral standpoint, you can also see similarities and differences. So much of the similarity, I think, is in the fact that although the brain is a neural network, which is kind of messy and entangled and has these weird kind of dynamics, it's able to engage in very, very, very structured forms of reasoning. So it's able to retrieve knowledge and make logical inferences, like, kind of knowing, for example, that if A is greater than B and B is greater than C, then you know for free that A is greater than C, right? That type of inference, which is called transitive inference, that type of inference is something which you can't just memorize it because nobody ever told you about the difference between A and C. You have to infer it from the data. And sort of magically, even though the brain is a mess, what comes out is highly structured and sensible. And neural networks, it's exactly the same, right? So despite the fact that the GPT-4 or your favorite language model has millions of parameters, nobody understands what's going on inside it. And yet, like, what you get out is these very structured forms of behavior. So there's a lot of similarity at the behavioral level. There's also a dissimilarity at the behavioral level. Dissimilarity at the behavioral level is like, when I wake up in the morning, I have a plan. It's like, I've got stuff to do and I try to spend my day doing it. That is not true for current language models. So current language models, they just sit there and, kind of like, if you query them, then they will respond because they're like autoregressive sequence predictors. But they don't have motivations. They don't have goals. They don't sort of intrinsically generate ideas about what they should and should not do and then seek to pursue them. But we do, and we do because we have to, because otherwise we wouldn't stay alive. So, as always, there are ways, if you wanted to make a case that neural networks and humans were totally dissimilar, there would be lots of information you could draw upon. But if you also wanted to make a case that they were similar, you equally would have, kind of like, the world's your oyster in terms of information.
Well, hello there. It's your host, Sam here. Now, I won't keep you for long. If you've been inspired by what you've been listening to today, and you'd like to find out what type of data storyteller you are, why not go to our data storytelling scorecard? Just follow the link to data-storytelling.scoreapp.com. That's score app with 2 P's. Answer 12 simple questions and you'll instantly be served with a scorecard that tells you exactly what type of data storyteller you are. Now, back to the action and our brilliant guest. Now, a former guest on Data Malarkey, Sylvie Delacroix from King's College London, who is a kind of lawyer and an ethicist. She runs the Centre for Data Futures. She talked a lot about the lack of humility markers in LLM's responses, kind of an absence of uncertainty, tendency not to know when to stop, and that still characterises some of the best models available. They're kind of unfamiliar with the Socratic paradox, that states that all that I know is that I know nothing. They and in that way, they some of what they produce is very unhuman-like. Can we train LLMs and other models to be humble, uncertain, and know when to stop, and I guess so be or at least appear to be more human?
Yes, I think you can, and kind of that is just a subset of the more general claim, which is that you can train or instruct these models to behave in almost any way that humans behave, whether it's kind of like desirable or undesirable. So if humility is a desirable quality, we can clearly provide training regimes that will make the models as humble as possible. Why are they not? They're not because they are commercial products and they are optimized for what their developers believe the average human wants. And the way that they ascertain what the average human wants is they pull a bunch of people who are like paid workers. They're often in kind of like faraway countries, often not paid very much, but what they do is that they view kind of alternate possible answers to a query, and they choose which one they think is best. And kind of like those raters are human, and so they exhibit all the biases that humans exhibit. And among those biases are preferences for certainty over uncertainty. So if you were to ask me a question and I was to say, here's an answer and I'm really sure about it and it's very clear and definite, versus another answer is like, well, I'm really not sure and I couldn't possibly answer and I don't know. You probably prefer the first one because you're human. So these raters also prefer the first one. And so they give feedback to the model that it should generate more answers like that. And so lo and behold, the model learns to satisfy that demand. And that's why the models that are then commercially deployed don't have that kind of humility. But it's not I think people would like to think that it's a sort of intrinsic limitation, because when models don't do something, or it appears that they can't do something, there's always a temptation to say, we've found it. We found the fundamental limitation, which is going to like fundamentally stall machine learning stops here. And it's always wrong. It's always wrong. There's always some other reason. And, in this case, I think it's just about what people want. And I kind of disagree with the idea that the fact that they're overconfident makes them unhuman. Like, actually, psychologists know that overconfidence is a sort of cardinal human bias. Most humans in most circumstances tend to be overconfident about their views on all sorts of things.
There's that wonderful stat, isn't there, that 75% of people believe that they're better than average drivers. I fit in the 25%.
Perfect example.
Yeah, I mean, I guess sometimes maybe when I get tired and I'm interacting with different models, I kind of feel that I mean, I'm not singling out any particular model. I've experienced it with several, but it can be a bit like a pub run bore. It can be in its overconfidence. But you're simply saying it's perfectly possible that if that were desirable and if that were commercially desirable, we could easily make them more humble.
Yes.
Maybe there'll be a humble toggle that we can switch on and off or slide up and down.
Yeah, I mean, I think it's important to remember here that you have degrees of humility, which is just like, what is the certainty with which you express your view, which you can, and we do this all the time. Like, we are naturally, depending on the audience, we will be more or less confident, right? I bet, an area that you're an expert in, if you're talking to a room full of school children, you'll probably be quite confident. If you're talking to, a room full of world experts on this topic, then maybe you hedge a little bit more, right? And we all do this. So, we can dial up or dial down the bias that is the degree of certainty that we express our views with. That is different from being accurate or inaccurate. So these two things often get conflated. The models are often overconfident about things that are wrong, and that's why it's a problem, not merely the fact that they are overconfident. And, getting the models to say things that we kind of agree are true is a problem. And it's a technical problem, it's a conceptual problem. The technical problem is largely one of how do we essentially deal with the fact that sometimes information is kind of just like a bit weird and hard to predict, and you just need to know it and you can't kind of make it up. And that's more true in some domains than others. That's a technical problem there. That's about how you do the sort of machine learning. Then there's a conceptual problem, which is much more interesting and much harder, which is how do we agree what's true in the first place? And I think there's been a sort of dramatic naivete on the part of machine learning researchers or AI developers in general. Obviously, what counts as true has been debated for thousands of years, and people haven't solved it yet. And I think there's some of the sort of boardrooms in which I sat, various, developers, it looked a bit like they thought that they would just put a committee of computer scientists on that problem and they'd just figure it out and then tell the models what to say. But, guess what? It wasn't that easy.
I'm sure not. I mean, I had a very interesting experience recently. Me and ChatGPT. ChatGPT did it. I just followed ChatGPT's instructions, I guess. But I mean, I was telling it what I needed to do. I was creating a business tool, a decision-making tool that had 6 different contingencies in it, and some were weighted in different ways. And we were doing this in Excel together. I say this as kind of obviously I'm embodying ChatGPT as being an individual here. And it was a long time since I'd programmed in Visual Basic, and I hadn't looked in the back end of Excel like that for some time. I did a doctorate in experimental psychology in Sussex about 20 years ago, and so that was about the last time I touched it. So it was like a sort of dim and distant schoolboy language, really, Visual Basic, but it came back quite quickly. And so I set out in quite a complex prompt what I wanted to do, and then refined that a bit, and then said let's go. And ChatGPT came back with do this, and this, and this, and do this, and here's the code, and paste it here and there. And I said, look, hey, could you just slow down a bit here? Can you just treat me as much dumber than you think I am? And can we do this step by step? And actually, for the rest of that dialogue, which was a day, it knew to treat me a bit more with kid gloves. And then when I was getting a bit more confidence or remembered that we'd done something, it would speed up a bit. Of course, the next day when I came back, it had forgotten that we'd had that conversation, and it had that inability to remember. Which I think some of the doomsayers feel that every single conversation is recorded and we will be remembered. And you suggest that it's kind of not like that, really.
Yeah, so technically it's not like that. So the transformer, because it is this, as I described, it's like it processes everything in this forward sweep. So it takes a chunk of information of a certain length and processes that chunk of information to predict what is the next thing in that sequence. So it's a chunk from a sequence, where that sequence might be a sequence of words or your pixels in an image or whatever you want. And that chunk has a finite length. And that is actually what makes it different from the brain. So in the brain, because you have this recurrence, so what the fact that in the brain neurons excite neurons excite neurons excite neurons excite neurons in a big loop means that in theory you can keep information around for as long as you like, right? So because the activity dynamics perpetuate themselves and they perpetuate the patterns, the representational patterns that are our memories. And so you don't have there's no theoretical limit, though there are practical limits, so no theoretical limits on how long you can keep information around. In the transformer, there's a hard cutoff. And what that means is that beyond that cutoff, without extra tricks, the model knows nothing about you. So this is one of the things that, kind of like will impede the models from, for example, really getting to know you in any meaningful sense, unless you give them other tools. So there are other tools which will do things like, you can probably see in some of the commercial models, there are like memory settings, and the model like knows something about you. And that's stuff that it's learned over your conversations, which is encoded in a kind of like notebook, which is like, what do I think about Chris or Sam or whatever? And then every time you have a conversation, that gets added in like a kind of aide-memoire. But yeah, I mean, the nice thing is that you get the opportunity to turn it off, right? So it would be quite convenient, if you had a really, you had a bad run-in with a colleague, it would be nice if you could just sort of press erase and like get rid of that, and they wouldn't have no recollection of it whatsoever. Start again the next day. But sadly, you can't do that in real life, but in ChatGPT you can.
Apart from in Men in Black with that pen that flashes and wipes people's memory, we need that. But we have that built into LLMs. You mentioned you were talking. I thought really interestingly about the fact that when we were talking about overconfidence, that with the real human coders who were so that's one of the reasons why. And I sometimes when I hear Tim Berners-Lee talk about what happened to his Frankenstein's monster, and the way that it became an advertising vehicle. I mean, I'm oversimplifying what the World Wide Web morphed into, but clearly. OpenAI and Microsoft and the rest of them are commercial organizations. Do you think it's inevitable that the models that we subscribe to are going to become advertising vehicles, or do you think they're rather more interesting than that?
Yeah, I mean, I think it depends on what you mean by advertising. So yeah, it's obviously true that many of the big tech companies that make these models advertising is their primary source of revenue. But it's also very interesting to think about what happens to advertising in a world in which, kind of like so much information processing is actually delegated to an AI system. And so, that is compounded when we actually think about, a world which probably is not very far away, in which the model not only tells us which shoes we should buy, but actually goes on to, your favorite e-commerce platform and buys them for you. And so in that world, advertising is actually quite useless because the consumer of the product is not making the purchase, right? So you don't need to advertise to the consumer. You need to advertise to their personal shopper, who is the model itself, right? And the way to do that is probably not to show ads, although it might be. The most effective way to do that is presumably to influence directly the developers to steer the model towards particular products. So as far as we know, this is not happening yet, but it does seem like it's certainly something we should watch out for. Like, it seems very plausible that in the future, where, kind of some future iteration of your favorite language model is no longer just kind of like quite useful for helping you with Excel, but is actually, planning your family holiday and booking it for you. and autonomously making choices, about, I don't know, which flight or which hotel, that some of the companies that own those airlines or those hotel chains might have tie-ins with whoever that developer is that steer you towards particular choices. And those choices might be commercially beneficial for that partnership, but maybe not what you would have chosen otherwise.
No.
So will that happen? I don't know. Could it happen in theory? I think so.
I was really interested in your book where you drew the parallel between what have been mislabeled, as you say, hallucinations in some, certainly in the earlier iterations of LLMs, as confabulations, and you draw the parallel with Korsakoff syndrome patients and what they do, alcoholic Korsakoff syndrome patients and what they do, in terms of that parallel with AI. Output errors. Could you talk just a little bit? Because I thought that was a really nice distinction, confabulation over hallucination. Can you talk a little bit about what that shift in terminology reveals about how we should relate to LLMs and their current limitations?
Yeah. So my main point there was rather pedantic, which is one of terminology. So psychologists already have a term for what language models do when they sort of make up information. That term is confabulation. Hallucination is something very different. It's where you have a sensory experience of something that is not there, and like that's typical of psychosis. It's very different. But machine learning researchers didn't pay attention to the distinction and used the wrong word, and now we're stuck with it. So that's the pedantic point. I think the more interesting point is like, why do models confabulate? And, kind of like you could see it as a sort of, and many people do, again, kind of see it as a sort of symptom of a fundamental limitation, kind of like these models are just never good enough. Oh, look how silly they are. They always make stuff up. And the argument that I make in the book is that the reason that they make stuff up is because language itself is a process of making stuff up, right? And like, kind of, although much of the sort of late 20th century natural language processing was premised on kind of quite a linguistic tradition which argued that the main goal of language was to convey truthful information to other people, right? Which is like a very kind of computer science way of thinking about the problem, right? Language is like a program, and when a sentence is like a program you execute, and the goal is to like convey some information to someone else, and like confabulation sort of like bugs in the program or something like that. But, of course, there's a whole other linguistic tradition going back to Wittgenstein, which says that that's not at all the goal of language. The goal of language is essentially contingent on what the social situation is. And we have very, very different goals in very, very different social situations. So, Wittgenstein called these language games. And, we as, so to give an example, the degree of license that you have with the truth depends dramatically on the exact linguistic situation that you're in. So if you're down the pub and you're telling a story, it's usually fine to like embellish a little bit to make it more funny. And that's because the goal is not really to convey the truth. The goal is to have fun and entertain your friends. But if you're in a court and you're giving evidence as a witness, then you better tell the truth, because otherwise you're perjuring yourself and you could be, prosecuted yourself. So the situations are very, very different. And the trouble is that language models do not experience those sort of social or normative contexts in the ways that we do, because they don't go to jail for perjury, right? So they don't have the same incentive structure. They don't have the same understanding of the fact that confabulation can be okay in one context, that is down the pub, and not okay in another context. So they just sort of do it a bit on average all of the time. And they do it in situations where it's like really, really strictly verboten. Like a classic example is like quotation or citation. Quotation and citation are two examples where we have just agreed kind of culturally that it is not okay to make stuff up. Like when you have the citation, there has to be a real citation. And that's a norm. It's a norm. It's nothing to do with the structure of language itself. It's just a norm. And of course, if you indistinguishably train the model on like Harry Potter and journalism and academic articles with citations, the models have enormous difficulty in working out that one part of that text you have to recreate absolutely verbatim. That's the citations. But the Harry Potter bit, we can make up stories about Harry Potter right, left, and center. Well, fan fiction, people can. So that I think is the root of confabulation, and people would like to make it out to be a fundamental limitation, but I really don't think it is.
That's good. That's very interesting. Now, looking back, let's sort of take a kind of helicopter view or kind of a wide angle here, kind of this and the sweep of cognitive science. Let's maybe go from Turing to transformers. What surprised you about how far we've come, and what still surprises you about how far, what we haven't got to yet?
Well, I mean, people have been surprised all along the way, including myself, right? So, kind of, I think the history of AI has been history of people saying that'll never work, and then it does. And, that's been true for many of the things that we've discussed already. It was true for chess, and it was true for Go, and it was, it's true for language, and so on. But I think the broader point is that what we have learned over that sort of sweep from Turing to today is that specifying the problem that we're trying to solve is almost as hard as trying to solve the problem. And what I mean by that is, like, when, at each of those milestones, each of those sort of astonishing, eye-popping discoveries, what's happened is, we've solved a problem. And then we look back and we're like, oh, well, that actually wasn't the problem that we really needed to solve. So in the to give you an example, in the late 20th century, it was widely believed among AI researchers that if you were able to train a computer to play chess at grandmaster level, then you've basically solved intelligence. And it's a reasonable supposition, right? It's because chess is basically one of the hardest things that people can do. Only very, very clever people get to be chess grandmasters. So, if you use chess as a way to just rank people in terms of intelligence, then you build a computer that can beat grandmaster. Then, well, of course you're superhuman. But of course, like, what's the problem with that argument? Well, the problem with that argument is that intelligence is multifaceted, right? There are many, many, many different aspects of intelligence. And the hard problem is not being good at one thing that is deemed to be, kind of like particularly important by virtue of the fact that those who we say are smart happen to be good at it. But the hard problem is to be kind of universally good at everything, right? And even language, which is clearly a sort of key which unlocks so many other skills, there are a lot of skills that it doesn't unlock, right? So it doesn't unlock, being able to cross rough terrain without falling over, right? Like, nobody can teach you that with language. In fact, there's a whole space of activities which, like, we are astonishingly good at, which, no matter how much linguistic instruction you had, it wouldn't make any difference. To get good at them, you've just got to practice a lot. Like we talked about tennis. You can't just read a book about tennis very, very carefully and then go out on court and play at Wimbledon, right? It's like you need to practice. So, kind of, I think what we've learned over the years is that we have privileged a certain set of activities which culturally and socially we thought were really important. And maybe those cultural and social values were also a bit self-serving, right? So, IQ tests, which today's language models are very, very good at. Those IQ tests, of course, were like designed by academics, and they were designed along the lines, they privilege the types of activities that academics are like very good at, like, maths and logic and verbal reasoning and so on. But when we think about what's actually hard, it turns out that the things that are actually hard are not necessarily the things that academics are good at or chess grandmasters. They're not even the things necessarily that humans are very good at. The really hard problems are the ones that, like, mice are really good at, like, crossing an almost, infinitely varied rough terrain without getting eaten or, kind of getting stuck or falling over. That turns out to be the hardest problem. But of course, it would be terrible to have to admit that actually the thing that is really, really, really hard to solve from a computational standpoint is the thing that other animals are better, as good or better than humans at, because it would just be very humiliating. So I just, obviously we don't want to admit that, but it happens to be true.
I I had an image of Daleks trying to go across a ploughed field or climb stairs as you were talking about that. Absolutely.
Perfect example. Yeah. Perfect example. Yeah.
Coming towards the end, I've just got a couple more questions, if we may. I really enjoyed your book, loved your book, and I think it opened my eyes in lots and lots of different ways. I thought there would be more about artificial general intelligence, AGI, in the book, and there are just 3 references. Is that because you think it's not likely to happen anytime soon? Is it an unattainable dream, or is it just around the corner, or have we been there for ages?
No, I mean, none of the above, I think. I think it's because I don't think that AGI is a very useful concept.
Okay.
So a lot of people, kind of AGI, artificial general intelligence, a concept we've sort of, AI researchers today have sort of grown up with as a sort of, the ultimate dream, which is to build a system which kind of essentially is as robust and functional in, the multiplicity of activities that a human can do. I think that today, we broadly think of, we often restrict it because we know that building embodied systems that can do stuff in the real world is both incredibly hard and kind of practically unattainable because of the physical constraints and regulations and all kinds of stuff. So you might think of that in a computer. Kind of imagine it's the pandemic. It's could we have a computer could we have a computer system, an AI that we could just drop in and do your job, right? You're a primary school teacher or an accountant or a lawyer or one of the many jobs that is teleworkable that you can do just over Zoom essentially or over a video platform. So, why is that concept not very useful? Well, I think it's not very useful because what we see from the development of AI systems is that actually, in some capacities, we can actually kind of sprint ahead and already get to sort of superhuman levels. And we are already at superhuman levels, undoubtedly, at things like reasoning and knowledge retrieval. That doesn't mean that ChatGPT knows more about physics than, kind of the world's most preeminent Nobel laureate. But it does mean that it knows more about it than most people. In fact, even the most physics PhDs now. Better at reasoning, so we have these superlative capabilities. But what we don't have is robust ability to do kind of multifaceted endeavors that require bringing together lots and lots of different skills, right? So, a good benchmark for me is for people who think of AGI as being really proximal is, what I could really do with is an automated diary manager. So diary manager is if you think of kind of the pecking order of teleworkable jobs, it's fairly low down the order, kind of obviously very, very important role for those who are doing it. But kind of it's something that we think of as, kind of maybe it's an entry level job for, someone, perhaps you don't need graduate training, whatever. And yet we're nowhere near having a model that can do that because the models, the skills that you need to do that require us to draw upon a whole range of things that we don't even think of as intelligence, but that are just essential. So to be a good diary manager, you kind of need to have a mental model of the person whose diary you're managing. You need to know a load of sort of social and cultural things about trade-offs and social hierarchies and the relative importance of different activities and all these kinds of things. Is that and so, of course, you can say, oh, well, kind of of course, an AGI would just sort of magically know all of this stuff. But I think what's much more likely is that we'll have systems that, for parts of that role, are amazingly capable. And in other parts, they just don't know the basics. So capability and robustness are very, very different things. So the latter I refer to as robustness. It's the ability to be fault tolerant, something changes. And, kind of you're able to behave sensibly. And so what is AGI then? Is AGI the capable system that makes silly errors 10% of the time? Well, 10% maybe doesn't sound like very much, but if it's doing 100 things a day and it gets 10 of them wrong, if it was a human, by the end of the first day, it would be fired already. So I don't find AGI a very useful concept. And I think that what will happen actually is that, kind of rather than us optimizing for building a sort of more and more human-like system, we will build systems that just themselves become more and more integrated into the technologies that we have. And what they will do is they will take the things that we do anyway, kind of like the technologies that we use every day, particularly, digital platforms, telecommunications, and to some extent the Internet of Things. And they will replace the rule-based systems that we have with like smarter versions that are optimization-based. And that integration into existing infrastructure is, of course, way, way, way more useful. But it's also not really like human-like in some sense of like, oh, we're building Stephen Hawking because, he's the smartest man alive or whatever. So, I think that we've sort of got the wrong paradigm for thinking about what the goal of AI is. And I think we should, the AGI, maybe it's useful to have a North Star. And I'm sure we can all use it as a proxy for progress. But I think the reality is quite different.
You absolutely brought to mind a former executive assistant of a former colleague of mine, and nobody understood until both of them left the business that the reason she had 3 different colours for the meetings that he had programmed at the same time, he would routinely have 3 meetings at the same time, was kind of gold, silver, bronze, but she used kind of red, blue, and orange. I think it would take an awful lot to replicate that. Thank you so much. Chris, now finally, where can our listeners and our viewers find out about you, your work, what you're up to online in social media and so on?
So I have a website, which I'm sure that we can maybe post the link alongside this podcast. Website, which advertises a little bit about my research and my books. And then there's a lab website where you can learn about my research group in Oxford, and you can also look up information about the AI Security Institute on the government web pages.
Perfect. We'll include all of those in the show notes. Thank you so much for your time today, Chris. I think it's fair to say if there were more people with your approach to using data smarter, there'd be rather less malarkey in the world of AI and rather more data-driven common sense. Chris Summerfield, thank you so much for being with us today.
Thank you, Sam. It was a pleasure. Thank you.